Welcome back. Unit 3, the advanced half of Solidity, and the moment it all becomes real. When we compile and deploy an actual smart contract with Truffle and MetaMask card, you'll have watched a contract travel from source code to a live address on a test network. Unit 3, Topic 1, Solidity, Mapping. Analogy, an infinite wall of code check lockers. Hand the attendant any key, an address, and she walks straight to that locker. No searching, no list. The same speed whether there are 10 lockers or 10 billion. This is Token Lite, a stripped-down version of the pattern inside every token contract on Ethereum. Its heart is one mapping. Line 2, the declaration, mapping, then key type arrow value type. Read it aloud. For any address, store a UNT 256 balances of Alice's address as Alice's token balance. One line, a locker for every address that will ever exist. Lines 4-5, mappings nest allowance of owner, of spender, answers how much did the owner authorize this spender to move, a spreadsheet with 2 lookups. This exact nested mapping is the ERC20 approval system moving billions daily. The require guard from Unit 2, does the sender's locker hold enough? Note the beautiful default, an address that never appeared simply reads as 0. There is no key not found error, every possible key already exists with an empty locker. Then the 2-step dance of every transfer, subtract from the sender's locker, add to the receiver's. Let's watch it with real lockers. State of the world, Alice's locker holds 100 tokens, Bob's, never touched, reads 0 by default. Alice calls transfer, her locker drops to 60, Bob's rises to 40, 2 storage writes, both behind the require guard, and either both happen or neither does, as the exception handling chapter will make precise. The exam card, mappings have no length, no key list, no iteration, and can't be returned whole. Why? Under the hood each key is hashed into a storage slot, Unit 1's fingerprints again, and the chain only stores slots that were actually written. The attendant knows the way to any locker, but there is no master list. Need a count or a list? Pair the mapping with an array, which is exactly what structs and our next topic make elegant. Unit 3, Topic 2, Solidity, Structure, Struct. Analogy, a printed form. A UNT is a single blank field, a struct is the whole form, name, price, seller, status, filled in, stapled together, and moved as one unit. Lines 2-7, the struct declaration. Item is now a type, like UNT or bool, but designed by us. Every item carries a name, a price, a seller address and a sold flag. 4 fields, 1 form. Line 9, compose it with Unit 2's arrays. An item array is the shop's catalog, a list of filled-in forms, in order. Line 10, compose it with mappings. Instant lookup of any item by its ID number, array for listing, mapping for finding. The two live side by side in almost every real contract. The list function creates an instance, item, parentheses, values in field order, name, price, seller, sold. There's also a named style, item, braces, name : value, clearer for big forms. The new form is pushed into the catalog. The trap every Solidity beginner falls into once. Fetch an item with the storage keyword and you hold a live reference. Editing it edits the blockchain itself. Price on chain, now 200. Fetch it with memory and you hold a photocopy. Edit all you like. The original form on chain never notices. Storage mutates. Memory is scratch paper. Choose deliberately. The data modeling toolkit is complete. Structs are the rows. Mappings are the indexes. Arrays are the lists. Next, controlling WHO gets to touch that data. Unit 3, Topic 3, Solidity, State Modifiers. Analogy, stamps in a function's passport. Each stamp declares what the function may do to the world, and both the compiler and the network enforce the stamps. 3 built-in stamps first, then we'll hire a bouncer. Stamp 1, view. The function promises to only read. Unit 2's get, carried it, called from outside the chain. View functions cost nothing. Stamp 2, pure. Stricter still, no state reads, no writes, just computation on its inputs. Our loopsine sum was pure. Stamp 3. Payable. The odd one out. It doesn't restrict. It permits. Only payable functions may receive Ether. Send Ether to a non-payable function and the transaction bounces. No stamp at all means full read-write power, and every call is a gas-costing transaction mined into a block. Now the custom stamp, the one you design yourself. Meet the vault. Anyone may deposit. Only the owner may withdraw. The enforcement is 4 lines long. The constructor runs exactly once, at deployment, and never again. It stamps MSG sender, the deployer, into owner. The vault knows its master from birth. Lines 7 to 10. A modifier, the bouncer. The require checks the caller's identity, and then the underscore. That lone underscore semicolon means the guarded function's body runs here. The modifier is a wrapper. The underscore is the hole the function drops into. Attach the bouncer by name. Withdraw is public only owner. Every call now walks past the require first. One word protects the function, and the same bouncer can guard as many doors as you like. And deposit shows payable in action. MSG value is the Ether attached to the call. In way, the function accepts it and counts it. No payable, no deposits. Live test. A stranger calls withdraw. The bouncer compares MSG sender to owner. No match. The require fails. The whole transaction reverts. The stranger paid gas for the privilege of being bounced. The owner calls. Match. Underscore. Body runs. Ether moves. Access control in one reusable word. This exact only owner pattern guards billions of dollars across Ethereum, and in the inheritance chapter you'll see how contracts inherit it ready-made. Unit 3. Topic 4. Exception handling in Solidity. Analogy. A circuit breaker, not a warning light. When something goes wrong mid-transaction, Solidity doesn't limp onward, it trips the breaker, and everything the transaction changed is rolled back, as if it never began. All or nothing, by design. Watch a 3-step withdrawal die at step 3. 2 state changes already happened. So are we stuck half done? Money deducted but never delivered? No. The breaker trips. Every change rewinds. 100 and 500 restored. As if the call never happened. This is why half-finished money transfers cannot exist on Ethereum. Now, the 4 tools that pull this trigger. Tool 1. Require. The input guard at the door. Condition false? Revert with the message. Refund remaining gas. Use it for caller input and state preconditions. This is 90% of real-world error handling. Tool 2. Assert. The invariant check. It guards conditions that should be impossible to break. Here, the vault must never hold less than it owes. If an assert ever fires, the bug is in your logic, not the caller's input. Solidity 0.8's overflow protection uses this same panic machinery. Tool 3. Revert. Same rollback as require, but as a statement you place anywhere. Natural inside if branches. Modern code often pairs it with custom, gas cheaper error types. Tool 4. Try catch. For the one place errors aren't fatal by default. Calling another contract. Our contract asks an external price feed for a price. What if that contract fails? The try arm. Call the external function. If it succeeds, its return value lands in P and the happy path runs. First catch. The external contract failed to require. We receive its reason string and quietly fall back to a stored price. Their failure, contained. Second catch. It panicked, or gave no reason. Same fallback. Without try catch, their failure would revert our entire transaction. With it, we absorb the hit and carry on. The exam card. Require for inputs, assert for invariants, revert for branches, try catch for other contracts, and behind all 4, the breaker, all or nothing, every time. Unit 3, Topic 5, Solidity, Inheritance. Analogy, family recipes. Grandma wrote the base recipe, mom inherits it, overrides the spice level, but still calls grandma's method for the dough. Nobody rewrites the whole cookbook, they extend it. Contracts do exactly this. On screen, the most inherited code in all of crypto, the ownable pattern. a base contract holding the owner logic, and a shop that inherits it. Ownable is a normal contract, an owner set at deployment, the constructor idiom from the Modifiers chapter. And our familiar bouncer, onlyOwner, written once, here, in the parent. Note one new word, virtual. It means children are allowed to replace this function. Without virtual, overriding is forbidden. Solidity demands explicit permission, no silent surprises. Line 17. The magic word, shop is ownable. That single is pours everything in. Shop gets the owner variable, the constructor behavior, and the onlyOwner bouncer, for free, without copying a line. Shop replaces describe with its own version, and must say override, virtual in the parent, override in the child, both required, both visible. If shop wanted the parent's text to super describe, calls up the family tree. And here's the payoff. Close is guarded by onlyOwner, a modifier shop never defined. It came down the family line. Write security once, inherited everywhere. The family tree, one ownable parent, many children, a shop, a vault, anything needing an owner. Real projects inherit these bases from audited libraries like OpenZeppelin rather than rewriting them. Inherited code is battle-tested code. Exam favorite, multiple inheritance. D is B, C, one child, two parents, one shared grandparent, the diamond. If B and C both override the same function, who wins? Solidity linearizes. List order matters. The most derived version runs, and you resolve clashes explicitly with override. B, C. Inheritance closes the language door. You can model data, guard it, survive failures, and reuse audited building blocks. Time to ship it to a blockchain. Unit 3, Topic 6. Compile and deploy the smart contract. Analogy. Compiling translates your recipe into the robot's language. Deploying mails the translated recipe to the world computer, which gives it a permanent street address. Let's follow VaultSoul on that journey. Step 1. Compile. As covered in Unit 2, Salt turns Solidity into EVM bytecode plus the ABI menu. Nothing has touched a blockchain yet. This happens on your laptop. Step 2. Deployment is just a transaction, with one twist. The to field is empty. A transaction addressed to nobody, carrying bytecode as data, is Ethereum signal. Create a contract from this. Step 3. The block is mined and the network computes the contract's permanent address, a hash of your address and your transaction count. Deterministic. Unit 1's fingerprints deciding real estate on the world computer. From this moment the vault is a citizen of the chain. Code on every node. Constructor executed exactly once. Immutable forever. The Unit 2 characteristics. Now with a street address. One practical note. Deployment gas scales with code size. Mainnet mistakes are expensive and permanent, so professionals rehearse on a local blockchain and a test network first. The tool for that rehearsal is Truffle. Unit 3, Topic 7, Introduction to Truffle IDE. You could develop contracts over a campfire, run the compiler by hand, build deployment transactions manually, test by deploying and praying. People did, in 2016. Truffle is the professional kitchen, a project scaffold for your contracts, an automated taste tester, a practice stove, a fake blockchain on your laptop, and a serving trolley that deploys everything in order. One honest footnote. The Truffle project itself retired in 2023, passing the torch to Hardhat and Foundry, but the workflow you're about to learn transfers one-to-one, to the terminal. Setup. Truffle installs once, through npm. It's a JavaScript toolchain under the hood. Truffle init scaffolds the kitchen, a contracts folder for Solidity, migrations for deploy scripts, a test folder, and one config file naming your networks and compiler version. Truffle compile runs Salt for you. Bytecode and ABI land in the build folder, exactly the artifacts from the previous chapter, no manual flags. Truffle test spins up a throwaway blockchain in memory, deploys the vault to it, and runs your checks. Deposits work. Strangers get bounced. Green ticks before real money. This is the step that separates professionals from headlines. And Truffle Migrate deploys. Here to development. Ganache. A pretend Ethereum on your laptop with instant blocks and fake Ether. Zero risk. Infinite retries. The migration script is 6 lines. Deployer. Deploy vault. Compile. Test. Migrate. The rehearsal loop. But to deploy to a public network, something must hold your keys and sign. Enter MetaMask. Unit 3. Topic 8. MetaMask and the real deployment. MetaMask is Unit 1's wallet, all grown up, a browser extension holding your private keys, locally, never on a server, with a drop-down to switch networks, and a doorbell. Whenever any app wants your signature or your Ether, MetaMask rings and asks you. And the stern warning from Unit 1, now personal, the 12-word seed phrase is your keys, and the keys are the money. Anyone who reads those words owns your accounts. Lose them and no support line on earth can help. Write them on paper, not in screenshots. The confirm dialog, dissected, the network you're on, the account whose keys will sign, the recipient, watch for the empty to meaning contract creation, the gas estimate, and the total. Read it top to bottom every time. Nothing on chain happens until confirm. The capstone, same migrate command, but the network is now Sepolia, a public test blockchain with real miners and worthless Ether. The dress rehearsal stage. Truffle builds the deployment transaction, and stops. It has no keys. Ding. The doorbell. MetaMask pops up. Sepolia network. Your account. Empty 2. A small gas fee. Unit 1's keys are about to sign Unit 2's transaction carrying Unit 3's bytecode. Confirm. The signed transaction broadcasts. A Sepolia validator mines it, and there it is. A contract address. The vault is live on a public blockchain, visible in any block explorer, callable by anyone on Earth. One more ring, we call deposit, with 0.1 test Ether, payable, from the Modifiers chapter, doing its job, confirm, and the vault's total reads 0.1. You have now watched the entire course execute in 90 seconds. Write it, guard it, test it, deploy it, sign it. The full toolchain is yours. Unit 4 changes the venue. Blockchains that run behind company walls. Unit 3, complete. And this was the big one. You can now model data with mappings and structs, guard functions with modifiers, survive failures with require, assert, revert and try catch, reuse audited code through inheritance, and you watched a real contract get compiled, tested, and deployed to a public test network, signed through MetaMask. Next time, Unit 4, blockchains behind company walls, private and permissioned chains, state machines, multichain, and the siege of the Byzantine generals, solved at last. See you there.